Welcome to part 2, number 9, with the coin on the turntable. I actually covered this one in the lecture video that you guys should have watched yesterday. So the deal with the coin on the turntable is, of course, it's got friction holding it into that circular path. Without friction, without friction, it would just sit there while the turntable spun underneath it. So it wouldn't be moving at all in the first place. But whatever, if say it were in motion, right, and there weren't enough friction to hold it in place, well, then it would leave the circular path and go sliding off the turntable. So friction inwards is what holds it into the circle, and we draw the centrifugal force outwards out of the circle. So my sum of x forces equation would look like friction minus Fc equals 0. All right, the sum of y forces equation we need, because I don't know what the friction force is. We're supposed to find the coefficient of friction. If all I wanted was the force of friction, I've actually got enough to go with there, right? Well, mostly. I don't know the mass of the coin, so I suppose I couldn't actually get the force of friction. All right, but if I knew that, I would be almost there, because I know how fast it's moving and I know the radius of its path. All right, but they want the actual coefficient of friction, which is why we're going to have to do friction is fun, as we have been doing for ages now. All right, so that means that I need the normal force. All right, well, I drew a side view rather than a top view so that I could draw the normal force and the weight. All right, so those are the vertical forces. N minus mg equals 0. All right, so that means that the normal force equals mg, which means that the friction force would be mu mg. All right, and so therefore I should be able to plug that back in here and get mu mg minus, this has never happened before, my phone's ringing during a video. Anyway, as I was saying, so the friction force minus the centrifugal force equals 0. Slide that over to the other side, and we can cancel out the mass. Thank goodness, because we didn't know the mass, and so we couldn't come up with an answer from that. All right, now that means that the coefficient of friction would be v squared over gr. If you did that, though, and you're like, I don't know, I didn't get the right answers. What am I doing wrong? Well, they gave you the things in stupid units, okay? And so you might have imagined that it's just going to work out and that you're going to be okay if you just plug them in as is. Because, hey, this is in centimeters per second. This is in centimeters. So it should be fine, right? The reason it's not fine is because g is in meters per second squared, and the velocity is getting squared. So that means that those centimeter units actually matter twice. So before you can plug in these numbers, you got to turn that into 0.5 meters per second, and this into 0.3 meters. All right, once you plug those in, everything should work out just fine. All right, let's try number 16 now. All right, for 16, they've got the roller coaster, so it's like what you did in the classwork. They want to know the normal force at the bottom. So just like we did in the classwork, you've got gravity down, normal force up, and the centrifugal force down, because the centrifugal force is always out of the circle. So you should be able to get it no problem as long as you are being careful and not messing up your signs. All right, so that means that the normal force at the bottom of the track would be whatever mg plus Fc is And since they give you the mass and the speed and the radius of that track, you should be able to plug the numbers in and get the normal force. And it's big, kind of like when we did the question with the car. All right, now this one, where they want to know Vmax. Again, this is very much like what we did on that classwork sheet, so it shouldn't have caught you by surprise. At the top, it's got gravity down, and the normal force up, and also the centrifugal force up, because it's got to go out of the circle. Mr. Errico, I have a question. I thought what we did yesterday when we found the maximum force is we said that the normal force was 0. So why are you drawing it in? Okay, very good, actually. At the maximum speed, the normal force is 0. That's why it's the maximum speed. If you went any faster than that, then you would leave the circular arc entirely, all right? So if you're going at the maximum speed, the normal force is just barely 0 because you're just barely skimming the top of that track. Also, this is a bad roller coaster. Like, there should be some kind of a safeguard so that you don't exceed the maximum speed. I don't know what they are doing there. But be that as it may. All right, so if we weren't told that it was the maximum speed, then what we would say is, for the vertical forces, N plus Fc minus mg equals 0. But since we're going at the maximum speed, the normal force is 0. And so therefore, just like yesterday, you should be able to get it down to V equals root GR. And then whatever that numerical value is for an answer. All right, let's see. There was one more question. That's number 19. So let's see if I can find that one. And no, that's not it. Sorry, excuse me. Pardon me. I don't know who drew that. Okay, here we are, much better. Okay, I hope that's not too hard to read in blue. We have, oh, this glare is really bad. Oh boy. Well, we have an archaeologist over some alligators swimming down below. Okay, it's kind of hard to see, but you can, I don't know, I think you can see it well enough to be able to get the rest of the question from there. All right, so we want to know, is he going to be able to make it, right? And they tell you the length of the vine and how fast he's moving at the bottom and how heavy he is. And then the unfortunate fact that the vine can't exceed a tension of 1,000 newtons, or the rope will, or the vine will snap, and then he will plunge downward into the river, where presumably there are man-eating alligators. Okay, so the sum of the vertical forces is what ought to be able to tell us whether or not he will make it. Pulling upwards on him, we have the tension. All right, pulling downwards on him, we have his weight. And if that were all, he'd be fine. He could hang from that vine and then be snapped at by the alligators for hours, presumably. But it won't snap if he's just hanging there. On the other hand, if he's also swinging, remember that's going to add some extra tension, because if he's going in a circular arc like that, then we have centrifugal force downwards. And so therefore, the sum of the vertical forces is tension minus gravity minus centrifugal force equals 0. Which means that the tension is his weight plus mv squared over r. And when you plug in your values into that, he unfortunately doesn't make it. All right, so the vine snaps. All right, I hope that's a sufficient explanation for the homework. At this point, you should now go to the instructional video in which we will talk about example 10.